All right, today our topic is radiant heating, specifically project estimating and installation. The way I'm going to go through this today is I have two different presentations from Rayhow, which is the manufacturer that we work with. Most of the information is applicable to anyone. That's just kind of what I'm using as my baseline here. And then to finish up, I'm going to go through some specific information kind of related to what we do here at TEC to help estimate jobs and help you, give you some starting points or rules of thumb. So without further ado, let me switch this over for you guys. Okay, and get this into full screen. All right, so as I go through this, please feel free to enter any questions in the questions or chat boxes. This is not for PDH credits, so you guys can multitask as much as you want, and we won't be stopping for any poll questions, so pardon me. So please feel free to type in a question in chat as much as you want, and if I get a couple, I'll stop and take a moment to answer them. So the first presentation, as I alluded to, is just going to go over some installation techniques and then kind of the procedure that you'll be taking, as you work on a job. And then we'll move into estimating and then some other things. So the first presentation, the overall outline here, we're going to go quickly through a little design overview. At this point, we're going to assume that the project has kind of been laid out already, and we'll touch on that in the second part of this webinar. We're going to review two main different installation methods, wet versus dry, and then manifold locations, step-by-step process, and some difficulties to help avoid. You always want to start your design knowing what the space is going to be used for and the heat loss associated with that space or the amount of heat you're putting into the space. If it's, floor heating or floor warming in a bathroom, you're not necessarily working with the heat loss. You're working based on just warming the floor. So once the heat loss is known, the designer can go through and select the installation technique and then the pipe sizing on all the associated pieces, the pipe ends and fasteners and whatnot. So this presentation, we're going to focus on the actual installation techniques, and then I'll touch on the others later. So the first part, we're going to focus on a wet slab. And this is where the poured thermal mass is wet, basically, Portland cement or other types of concrete or lightweight overpour. And there's two main ways that we'll address this. One is a poured slab that as you would normally think of it, and the other is an overpour with gypcrete or other lightweight, as you can see with the guy on the right. One quick other note, a lot of times nowadays slabs have different ways of installing the the reinforcement in the concrete. This example here, Dramix, is using wire fibers, and you always want to check with the manufacturer first, but in most cases, none of these products will hurt the pecs at all. In general, when we're working with a heated slab like this, this is what your layout's going to look like in a cross section. You're going to have installation on the bottom, the pipe fastened either to the installation or to a wire grid, and then the poured slab going over it and around it. You usually want to fasten the pipes every 2 feet, 2 to 3 feet to prevent floating. you're going to have a maximum fluid temperature based on the concrete itself and the surface temperature. Usually 140 degrees is the max. That's more of a snow melt number. Usually with radiant heating, it's going to be a bit lower than that. But as it lists here, the important note on this slide would be for thicker slabs, like 6 inches and above, you really want to install the pipe in the middle of the slab. In a smaller slab, 5 inches and below, usually just install the pipe at the bottom. This is kind of another look at the same thing. I'm going to kind of skip through some of these slides just to save on time here. It's very important to insulate below the slab if at all possible. In some certain cases, especially with snow melt with pavers or asphalt, where drainage can be an issue, we usually do not use insulation. But especially in a heated slab indoors, you always want to insulate below and on the edges if at all possible. For minimum, as you can see here, they're showing R5 below and R10 on the sides. There are other types of insulation as opposed to a standard foam insulation, such as like a CoverTech. If you've ever done a job that TEC's worked with, we'd use a lot of the CoverTech R foil insulation, which is like a poly with a foil layer. Those don't necessarily have a traditional R value as high. I think it's usually like 3.8, but they have a aluminum reflective barrier, which helps. So in either case, you do want some form of insulation. If you're doing a joist-based insulation, as I'll touch on in a little bit, you want an increased, you definitely want an increased insulation value to make sure you're driving the heat upwards. Here's another look at the same thing. Make sure you're using edge insulation and bottom insulation, especially when you're working on grade. Here's another example just of how you want to do your edge insulation. All right, fastening technique. The first and probably most predominant would just be to use nylon ties to the wire grid that the concrete's getting poured into. This is obviously probably the most cost effective. It is a little time consuming and you got to be down on your knees working with it, but it's definitely, you know, tried and true, cheap and easy way to do it. If you're getting into larger commercial type applications, it can be quite tedious. So there's other options that you can look at, and we'll go over a couple of different options here. But this is definitely the one that is most widely used for sure. Quick note on those: make sure you're snipping off the ends of these and collecting them in a box so they're not floating around your concrete. Another very popular technique, and probably one that you come across a lot, would be a foam staple. These have definitely gotten better over the years. They, you know, weren't always the greatest at sticking in and actually holding the pipe, which can be, you know, an animal sometimes. So they've definitely gotten a lot better. This is a very easy way to do it if you have the tool, but you need the tool in order to do it. So definitely a good option if you're going to be doing a lot of radiant work. There's a nice sample install of that. This is in a larger commercial area, same deal. Another option, this is Rayhau's version, Railfix, but most manufacturers have a similar thing. It's just a track you put down every couple of feet, and then the pipe just kind of snaps into it. This is another nice option. It is more expensive, but it makes for a nice, clean, and easy install, and saves you some backache. This kind of deviates from the fastening techniques here for a sec, but another related installation when you're setting up your grids is you want to protect the pipe with an extra measure on any control joint or construction joint, or if you're pouring the slab in different parts, anytime the pipe crosses one of those junctures, you want to put one of these PV protection sleeves on it. Again, Ray House sells their own version. You can buy these at a hardware store, or other manufacturers probably have their own version. All you're trying to do is make it so that the portion that goes through the crack, you're basically elongating the area that the pipe is going to get stretched through and preventing it from any abrasiveness over time from heating and contracting. You don't want the pipe to be rubbing on something. So it's just an extra measure to make sure the pipe itself is still resilient these days, that it's just an extra measure to help it. So when it's lasting, 30 plus years, you want to take any precaution to keep it that way. Here's a nice, you can see they're going to be pouring one side first, so they got the little protection sleeves on there. Again, also on that note, if you know where the joints are going to be, you want to do your best to run the fewest passes through the actual joint. On that previous picture, you'll note that they could have easily just gone the other way here and just had one or two little intrusions. Instead, they had all of them, kind of like the top picture here. So when you're designing or when you're designing or laying out the piping plan, you just take the extra time to think about, where your control joints are going to be, where your manifolds are going to be, as we'll talk about later. And, with radiant especially, as in most HVAC related work, if you just take a little extra time planning it ahead of time, it'll save you a whole lot of headaches. Again, on the same note, if you know you're going to be planning a saw cut, or if another contractor is going to be drilling in a certain area, mark all that out ahead of time and plan your piping accordingly. This is just a quick note on suspended slabs. If you're going to be pouring, this usually happens in commercial junctures, but if you're going to be pouring in a floating or suspended slab, no problem with the PEX. The structural engineers are going to have a say in it, and a lot of times they'll question how much pipe you're running through there, and just need to know exactly what's going on. But the pipe makes up such a small cross section of the concrete that you're really not disrupting much. And depending on, if you're using it for heating or cooling, you have to be cognizant of the space below, either putting up foam board below it or spray insulation, unless it's intended to heat both ways. On a lot of new projects where they're using them for heating and cooling, they'll be putting the PEX in the floor and ceiling slabs, and basically it's using it to offset the heating and cooling in both zones to bring down the heating loads or cooling loads. This is just touching on what we just mentioned there. I mean, for a 12 by 6 inch cross section of concrete, it's 0.8% of the cross section, so you're not displacing too much here. Couple quick things to note, again, with the fasteners and how you're attaching them. There's going to be a lot of other potential hazards, so you want to be careful with your fasteners, obviously, but also if you're going to be carrying a lot of stuff over them, plan ahead of time, put down some boards or whatnot. The PEX can take a beating, but there's no reason to rough it up if you don't have to. Be cognizant of, sharp zones from metal rubbing. You don't want it to sit up against anything sharp, because over time, expansion, contraction, it could just slowly rub on it. Not something you want to risk. Okay, we're going to switch real quick here into a suspended wood overpour, which is the other type of wet installation that we were talking about. You can see here on the bottom right, It's common to have them with sleepers if you're going to be putting a wood floor over them. Otherwise, just a standard poured slab over the wood. There's going to be a couple different fastener options here. You can do it with the grid as we showed before with wire mesh, or you can staple as shown on the bottom here, talons up at the top. If you have the luxury of knowing that you're doing this ahead of time when they're building the house, you want to put in an extra base plate, and with a size larger so that you'll have nailing marks for carpet or flooring, whatever it is, against all the edges, and you'll still have your base plate on the wall after the slab is in. As I mentioned, staples are the most common, but there's a lot of different options. This is obviously your best case scenario where you can nail it from a standing position. Here's a nice look of a larger area. They've got them all taloned out, nice and straight. That, of course, is a nice organized layout. They don't always turn out that way, but here's another one using the rail fix that I mentioned earlier. Again, that's Rahow's name for this track. Most manufacturers will have their own version of this. Again, it makes for a nice, easy layout. This works well if you have these larger square areas like this. If you're getting into a home or zones that have a lot of smaller different walls and angles, this can start to be a pain. But if you're doing an open area like this, it definitely makes it easy. Just as I mentioned before, the insulation is always a big issue, but when you're doing a suspended floor like this, it's magnified. As you can see here, below, with a heated space below the system, you want at least 5 times the R value. So that would be the subfloor and the flooring above. 5 times that value in insulation below with a minimum of R5. If the space below is unheated, like a crawl space or something, you want 10 times the value of the flooring and the subfloor. So those are 2 important numbers to note right there. 5 times the R value. There's a heated space below, 10 times in an unheated space. Here's a couple installation pictures. One thing to note, for a gypsum cement overpour, the wood floor has to be sealed beforehand, and I believe it's, yeah, here we go, with a Portland cement overpour, the subfloor has to be covered to prevent bonding. So you just need to be cognizant of what medium you're using. Usually you'll be working with a concrete guy who's going to be pouring it over your tube, and you can work all this out ahead of time. But just another thing that to be cognizant of, and another thing that pre-planning will help alleviate some headaches. As I mentioned at the beginning of this section, it's common to see it with sleepers, so that you can fasten a wood floor to it without messing with the floor. As it notes here on the bottom, though, depending on how long it takes the concrete to pour, it might be a while before you're allowed to install certain hardwoods. So just in summary of our wet pours, proper insulation, pick your fasteners according to your installation type, and proper planning and preparation is always going to save you the most headaches. Quickly going to touch on the layout patterns that you can use. The first is a serpentine, which is just a back and forth. It's probably the most common that you'll see. The other would be a counterflow. Let me see, I think I got a graphic of one of these. Here's a couple. This is just what serpentine looks like, as you'd expect, with an L kind of put into it here. The one thing to be careful about is just to make sure fill in any gaps so you're not getting cold spots as they show here. Going through a window. Okay, here's a counterflow. This is the best way to describe it as a spiral, but basically the supply and return are following each other as they wind into the center area here. And this gives you the most even temperature distribution across that area. You really can only do it when you have a kind of a boxed area. You can adapt it to other shapes, obviously, but the easiest way to do a counterflow is when you have a bigger area like this. And like I said, best temperature distribution. Here's another larger area. As you can see the different spirals. Now, what's most common is kind of a combination of the two. When you have outside walls, you want to do a little closer spacing, and you want to run the hot water in on the outside first. And so here's a pretty common example where you have a zone in a corner of a building. So they run a couple passes with the hottest water on the outside and then go into a combination where they do the counterflow spiral in the middle. And here's an actual example of what that would look like. Going across the perimeter, a couple strokes, and then coming through the middle. A lot of times, as you can see in the top corner of this picture, when you have closets and hallways, you're going to end up having to kind of figure out your own way to get it distributed properly based on the layout. And you know, a lot of times manufacturers, Rayhow included, will do drawings after the job is finalized for installation. They'll do the tube drawings. But a lot of times when you get on the actual job, you're going to have to make some adjustments based on the actual area. So as you can see up in the corner here, they've gone back and forth and around a little bit kind of to fill that space in that closet. And that's perfectly acceptable and normal. All right, now we're going to switch over to the dry installations I mentioned. These will be mostly, mounted in joist spaces below. There's a couple that are installed above that we'll touch on as well. So there's no poured cement here or any heat mass. Your thermal mass, if you will, becomes the air gap between your insulation and then the plates, the pipe, and the subfloor are all included in there. Using plates do increase the thermal efficiency of these underfloor systems quite a bit, and you don't have to run quite as hot of water. Typically, your max temperature is 160, although usually, again, that's a lot lower. Ideally, it's a lot lower for more efficiency. Installing them without plates, though, you're really limiting the amount of output you can get out of them. Even with plates, you're probably looking at about 20 to 25, maybe, if you have a good plate system intact, BTUs per square foot. So this is most common in retrofits. Usually, if you have a new construction, you do not want to recommend this type of installation. But it is, if it's done right and it's insulated correctly, it can be an effective way to heat the floors above. But installation is definitely key in these. As it shows here, pros, retrofit, no structural weight added, no added moisture. And then cons, as it shows, difficult to install, especially if there's pipes and everything running below. Installation is critical and slower response times. So here's this specific panel they're showing is the ROW plate from Rayhow. Again, one of several of their own heating plates, and then one of several million from different manufacturers. This is a nice little system, though. It holds, as you can see here, 2 runs of 1/2-inch pipe. And then you're going to leave an air gap install your installation, preferably with a foil face, and then maybe even additional insulation below that barrier, depending on the space below and the flooring above. Here's a cross section of what that looks like. Rahal also has two different lower cost options. Depending on the size of the job, these are definitely acceptable. They're a little more time consuming to set up and a little less heat transfer, but definitely more options. Here's the route plate I mentioned. I won't spend too much time on these. This is just showing the increased efficiency of using the plates. Again, this applies to all manufacturers, not just Rahal. More route plate installation. This is another what it looks like. Basically, you're just going to be running it back and forth, pretty typical, and then bringing it over to a manifold. The one thing you want to keep in mind when you're doing these, and we'll mention it a little later when we're going through the estimation, but when you're doing joist space installation, you have to account for a lot of extra piping for the tails. As you can see on the top portion of this, all the piping has to get run back through to where the manifold is, which is the case of all layouts, but these tails aren't taking up floor space, which they will typically do in a regular installation. More route plate specific. Again, with most heating plates, going to be careful how you cut it and make sure you deburr the edges to make sure it's not messing with the pipe. Here again, this is showing the lighter heavy gauge plates where you have to hang them individually for each stripe of pipe. And then as it shows here, you want to make sure the ends are loose for thermal expansion so there's no noise when the system's going on and off. And with these plates, you have a choice between 3/8 and 1/2 inch tubing. That route plate uses 1/2 inch. Again, with all these, be careful of sharp edges, wear protective gear, be careful with fiberglass installation, and of course, ladders. Here's a couple install pictures. This is nicely done. This is obviously pre-installation, which is key in these systems. But as you can see, the route plate makes for a nice little system there. Here's one with the light gauge plates. Again, a lot more labor to get those in. And again, these are pretty clean looking, not too many pipes in the way. Depending on what basement you're walking into, these could be quite a nightmare. Here's the heavy gauge plates. Difficult installation. Zoning is difficult because you're following the joist spaces. High insulation is critical. Higher water temperatures, slower response times. Nothing we haven't really touched on. Okay, let's transition slightly here just to discuss where we're going to be putting our manifold locations. So typically in a smaller commercial or a residential setting, each circuit is going to cover about 250 to 300 square feet. If you get in a larger commercial, that can go up to about 400 square feet. And we'll touch on some of those a bit later. But you got to remember that all of these zones are coming back to manifolds. So how many manifolds you use and where you locate them are key. And it's one of the first things you want to discuss when you're looking at a radiant job, because you need to be able to run the pipe to something. One of the main considerations is, especially in a house or a floor of a building, are you going to have one central manifold, or you're going to have a couple smaller ones for different areas? And that also affects how you're going to zone the system. If you have one temperature zone versus several, it may affect how how many manifolds you use. These are some larger ones. Well, the one on the left here is just a 6-loop manifold, but these other two are quite large. They look like 10-loop manifolds. So you just got to be cognizant of where you're putting them. You got to have access to them. And then as you'll see on these two on the right, you have a lot of piping in a small floor area. So when some of the zones are kicking on, this area is going to be, kind of a hot zone. Not necessarily, it could be, depending on how the system's zoned. So another thing to be cognizant of, if you're going to be splitting this up into a lot of separate zones, you may want to use separate manifolds. So here's just a quick example of a residence. They got having two separate manifolds here versus one centrally located here. And as you can see how they've started drawing in, a lot of the piping is going to be coming back through this little entryway, which an entryway is the best place to do this if you're going to use a centrally located manifold, because it can usually use the extra heat, if there is any at all, from having the pipe run through there with the tighter spacing. But as you can see here, they're zoning it with thermostats in each of the areas, but all the tubing is running through one. So in that case, you'd use manifold actuators, which we'll touch on a little bit later as well. And then here's a live example of that one we were just looking at, with all of the piping running back to this front manifold. A lot of the times, how you distribute from the manifold is going to be based on the zones themselves. So for example, this is a school. You're probably going to have one in each classroom. So you see here you have 3 4-circuit manifolds and then one smaller 3-circuit on the top. Depending on how they're going to be zoned, again, and where you're able to locate the manifolds, you may have to do 2 classrooms on the same one, for example, with actuators on the manifold to split them up. But a lot of times the environment and your zoning will determine how you want to split these up. In this case, this is another school, probably a gym. They got 2 manifolds, one on each side. In this case, you could easily do one large manifold on this from the left machine room and go across. They chose to split it up here. All right, we'll do a quick step-by-step the installation process now that we've discussed some of the different components. And this is all covered. Rahal has their own installation guide. Some of you may be familiar with, but I'm sure every manufacturer has the same thing. So we'll go through this quickly. I know it's getting late in the hour. Locate the manifold, the first step. You want to mount the manifold in its final position. You may have to create a temporary temporary holding mount for it, but you want to get the manifold mounted first, and go through some examples here. You can mount the manifolds in any orientation. This shows it sideways, upside down. You can fit them just about anywhere. They can lay horizontally in a floor or in a joist space below. Ideally, you want to get the pipes nice and lined up underneath it, but depending on the actual design and where you're locating it, it's not always possible. The next step is to get your PVC beds in order. These are obviously some nice, pretty options here, where they've lined them all up with some unistrut and some clamps. This is definitely the best way to do it. Makes it nice and neat. Next step is to connect the supply side of your first loop, and then you can start running the pipe. If you're doing quite a lot, you might want to use an uncoiler. They're a bit expensive. There's some other options where they lay them horizontally on the ground that are a bit cheaper. But as you can see here, these guys got one or two guys helping lay out the pipe, and then the rest of the guys are fastening. You want to start with the zones that are on the outside wall and then work your way back in. You want to keep the pipe 6 inches away from the walls, any holes or cabinet mounts. You also want to avoid toilet wax rings. You want to leave a little extra room around those. You don't want to be melting that steel. All right, another standard. You want to attach the pipe every 2 to 3 feet using whichever fastening system you're using. Ensure the pipe is straight and doesn't lift out. If it seems to be lifting up, just use an extra fastener. Make sure to avoid any weak area or any areas that you're going to be doing cuts in the concrete, or any control joints that you're using the sleeves that we talked about. Again, avoid walls, cabinet mounting points, toilet flanges. As I just mentioned, install protective sleeving for any exposed areas. And if you accidentally ding the pipe or make a cut in it, you'll have to replace it with a fitting. Ray Howe has the Everlock system, which is approved to be buried in a slab. You just have to wrap it with silicone tape, basically electric tape, to keep it from corroding the brass. But otherwise, the fitting's approved for being mounted in the concrete. Then after you lay that loop, you'll bring the return back to the manifold, and then go ahead and continue laying your tracks. After that, you're going to want to pressure test the system. So the easiest and best way to do this is just an air test. Again, this is Ray Howe's version. They got a little kit that hooks onto the end of your manifold. Bring it up to air pressure. You want to pressurize the first time, and then after like 10 minutes, pressurize it again. Make sure that it's up to pressure. That after the pipe's stretched out a little bit and everything's all set, then you want to keep that pressure for 2 hours. And then you'll want to keep it under pressure again when you're actually pouring, so you'll be able to tell if they cut one of the tubes, so you can quickly repair it and then get it back under pressure. All right, this is just showing the air testing kit plugged in again here. If they have air vents on the manifolds, you want to make sure that either disconnect those or seal them off. You can also fluid test. You have to go through. You're going to want to go through and purge each of your tubes once the system is getting filled anyway. But you can do this to pressurize it before the slab is poured if you want. This is just showing you can go through and isolate each of the loops, purge all the air out, go one by one, and then go ahead and open the whole thing up and keep filling. Just some quick precautionaries: make sure that the pipe is free of kinks and punctures, make sure it's properly fastened, and if you're using staples and whatnot, make sure none went through a piece of pipe. Cover any exposed pipes that you want to keep clean. Pretty straightforward. Clean wooden bridges for wheelbarrows. Just more common sense things, you know, if you're going to be running stuff over the pipe, cover it. Protection sleeving where needed. Pipe is pressurized and holding pressure during the pour. Nail guards are installed where needed. For system startup, you want to make sure that your concrete is cured. Check with the concrete guy on that. You want to start with lower temperature water. Obviously, you're just going to pipe in the city water and then bring it up to temperature. Here they show raise the temperature, water temperature by no more than 10 degrees per day to prevent thermal shock. So check with the concrete guy again on this. and proceed accordingly just to make sure that you're not messing with his slab. Then you're going to go through and you're going to balance the flows based on what was calculated for each zone. Most manifolds these days are pretty easy. Ray House, you just pop the little protective cap off and then dial it in with the little key, and then you can see the flow on the top, and you'll just dial in the flow that was required, which is obviously based on the heat that was required for that zone. If you're using zoning actuators, those replace these little protective blue caps that are shown here on the bottom. So you'll mount those, you'll dial in your flow, and then the actuator will mount right on top of that. Here's a couple of what not to do things. Just make your manifold stations look nice. Your customer's going to be looking at these obviously, and it's going to, reflect on your work obviously, but also people that are coming back to work on it in the future. The nicer and neater it is, the easier it is to work on, the longer it'll last. Bring your pipes back in an organized fashion. Here you can see they just brought them all in a big group at the bottom. You can mount the manifolds upside down, so you don't need to be doing these giant loops like they did here. This guy seems pretty proud of this job that kind of got off track, to say the least. And the spacing is very huge, specifically so you don't get streaking in the floor and hot and cold spots. This one is obviously a disaster. All right, and we'll quickly, I know we're running short on time, let me get into our other presentation real quick. We'll go a little quicker. A lot quicker, just kidding. All right, so we're quickly going to go through estimating. You have a lot of different pipe sizes to choose from. The key here for pipe sizing and spacing is the flow required. So based on the heating required for each zones. If you're doing snow melting, you're going to be in a much bigger diameter than you are for a small floor heating zone. For residential circuits, you want to stay at or below 8 feet of head loss per circuit. In snow melt systems and larger systems, you can tolerate a larger size, but you don't want to be putting a big circulating pump in a small residence. And in general, you're going to weigh the cost of running a bigger circulator for the next, 50 years versus the cost of bigger pipe. So rating in general is a bigger upfront cost, and so you might as well make it so that the system will be operating more efficiently going forward, is my personal take on it. Just go ahead and use a slightly larger pipe if you have to, or shorter circuit lengths. As you can see here, 1/2 inch is the most commonly used. It's used on pretty much any residence or light commercial wet system in most joist-based systems. 3/8 and some other smaller unique sizes have been becoming popular for dry panel systems. I didn't really mention them in the install, but I'll touch on ROW panel and ROW board, which is something that is used as an overfloor installation technique. Let me get this in the full screen real quick. And you can see here, the larger pipe is also going to have a larger water volume, which is something to keep in mind when you're doing your expansion system. All right, so your pipe sizing and quantity is going to be affected by the project type, the installation technique that you're using. Perimeter and occupied areas, we'll touch on in a sec, the differences there. The spacing of the pipe, obviously, square footage of the area will determine the length of the pipe that you need. And then you're also going to be choosing based on, the coil lengths that are available from the manufacturer. One thing to note here is that you usually want to be running a tighter spacing between your tubes at the perimeter of a building versus a general occupied area in the middle. As we'll show here, Rayhouse will have you calculate the areas separately, but as we'll show, in general, all you want to do is just slightly overrate your square footage area to make a quicker calculation. Here's some quick estimating methods. These ratios on the right here are just based on the spacing. For a joist space, since you're going to be running 2 lines in each joist space, we're assuming that you have a 16 inches on center joist space, which is going to give you 8 inches on center pipe spacing. That's also a common use for snow melts. We use 9-inch here, which is basically dividing by 0.75, as I'll show you in a sec. But at any rate, for different pours and different spacing, you're going to have different pipe to area ratios. And so you can see here, all we're doing to get those is dividing by the spacing for a 12-inch area. Okay. So for our first sample here, let's say we got a 40-foot by 40-foot just square building. As you can see here, they're accounting for a 3-foot perimeter area. So you calculate the areas of the different zones, calculate or determine your pipe spacing, and then you'll be able to get an estimate of the area. So we have an available area. They're taking 90% essentially, assuming that you're not going to be able to put radiant where there's already walls and plumbing and whatnot, which is a very good estimate. And then they've calculated for perimeter and occupied areas, and then you have a total area total amount of pipe of 1657. So this is kind of the long way to do it. The quick way of estimating would just be to say you have a slab that's 1,600 square feet. You take a pipe area ratio for a commercial slab of 1.1, and you got 1760. So you've only overestimated by 6%, which is pretty acceptable. I'm going to give you some quick, starting numbers to use here at the end that'll help kind of simplify this even further and make a little more sense here. This is just another for a residence, 2,500 square feet, doing a thin overpour, probably with 8-inch spacing, so they're using 1.3 here. And again, just 2.5% over, if you did the long calculation. Fastener selection, as we talked about in the installation portion of this, is obviously going to affect your estimating process. So we've calculated the amount of pipe that we need in linear feet. Now we got to estimate the fastener requirements. This is obviously going to depend on the type of fastener or installation you're using. If you're using nylon ties or clips or whatnot, we estimate these at every 2 feet. You can usually spread them out a little more towards 3 feet, but then you're going to need extras on the end. So if you do every 2 feet, you're basically just dividing your linear pipe length by 2. It's the quick and easy, dirty way to calculate it. For the rails and different manufacturer-specific installation tools, any of their installation tools will tell you how to estimate the figure. So for example, if you go to Rayhouse website and pull up the rails, it'll say, multiply by 0.45 to calculate the number of rails or linear feet of rails you need. And I'll show you how to get that information in a sec. As I said, just divide by 2. So for our example before, 1760 feet of PEX pipe divided by 2 is 880 ties, clips, whatever it is, staples. Again, going back to what we mentioned before, it's going to depend on how the manufacturer is selling them too. So And as I mentioned, the rail fix, each piece is 6.6 feet long, and you need one for every 20 square feet. So for this specific example, it would have been 80 pieces of rail. And as I mentioned, you can find those on the information provided for each of those. As we mentioned in the installation portion, which kind of manifold do you need? Most manufacturers offer a packaged Pro Balance manifold, as Ray Howe's version shown here. These are the easiest and best way to do your radiant manifolds. For as far as estimating, it's going to be based on the number of circuits, and then as we discussed in the installation portion, you can have multiple smaller manifolds or one larger. So you're going to need to know that to pick and estimate the manifolds that you use. You do have different options. If you're doing a radiant flooring, heating, whatever it is, you're probably going to be in a standard manifold. Ray Howe's Pro Balance is 2 GPM per circuit. You're not going to be exceeding that unless you're getting into snow melt. Sorry. This lower manifold, the XL, allows you to go up to 4 GPM per circuit. So if you get in the larger snow melts, you're going to need to be in a bigger manifold like this. You can also use these bigger manifolds to kind of be a sub-manifold back in your mechanical room. So you could put an actuator on each of the returns and then have the supply and return just run out to smaller Pro Balance manifolds in each zone. So it's a nice little way to zone it. You got the balancing all built in, the flow gauges all built in, supply and returns all built in. Makes it really nice to install. The other nice thing about these Ray Howe ones specifically is you can completely isolate each loop. So if you ever had a problem with one or you needed to purge and everything, you can completely isolate from the isolate at the flow gauge and at the balancing valve at the bottom. And then they have the air valves on the end. That's pretty common for all manifolds, the drain valves and supply and return. Again, one large manifold versus several manifolds. Case can be made for either one depending on how you're zoning and how the building's set up. How many circuits? This is going to be based on basically the pressure drop for each zone. So the key things to consider here are first your square footage, obviously, but then the flow for each that each circuit is going to see is going to be dependent on how many you have and how long they are, and then if you're using glycol. So here are some pretty standard methods. I would say these are for water only and for radiant flooring. Radiant heating versus snow melt. So these are all pretty common. For 1/2 inch, I would say that should probably be more like 300. 330 is definitely accessible. You're just going to have a slightly higher head loss than you probably want. So depending on how the loops are getting grouped for different rooms or zones could cause you to do a smaller 200-foot loops of 1/2 inch instead of 300. Again, perfectly acceptable. You just have to know ahead of time how you're going to do this so that when you go to order the pipe and the manifolds, you know how many circuits you have. And as you see here, they're just saying you take the total footage of pipe, divide by the number of circuits, and that's the minimum number of circuits you have. You can always add more based on the zoning. So if we go into a quick example here, we calculated for our 1,600 square foot slab on grade example earlier that we had 1,760 feet of pipe. We're going to use 330-foot circuits for this example. So we have 5.3 circuits. So at the very minimum, we have 6 circuits for this project. The next would be the manifold connectors. You may think, why don't these come with a manifold? But they're dependent on the size of the pipe you're using. So that's why they're interchangeable. Pardon me. Let me go back to that. You need one for the supply and return. They usually come in a package together. So you just need to count up the number of circuits you have, and those are the number of manifold connectors you need. That I'm assuming is pretty common across all of the manufacturers. That's definitely the case for array house. So if you're calculating for a array house specific job, you just total up the amount of circuits you have, and that's the number of connector packages you need. The next thing you want to calculate is the pipe bends. These are essential for going up to a manifold or down, depending on how you're installing them. They also help protect the pipe coming in and out of a slab. Even if you're not using a slab, they're very helpful. There's also metal bracket ones that are available, but the PVC bends are definitely the cheapest and easiest to use. These you're going to want one for each supply and return, so you just total up the number of circuits you want and then multiply by 2. All right, so we're back in our material estimate example. We've calculated that we have 1760 feet of pipe. They show here by 1800 feet. This is really going to depend on your circuit length and the tubing sizes available from the manufacturer. I mentioned 300 feet before. Half-inch pipe is sold in 300-foot lengths. You can just buy the number of circuits you need. Makes it nice and easy. The ties, in our array house case, they come in packages of 2,000, so makes it nice and simple. In this example, we had a 6-loop manifold, so we need 6-loop manifolds, 6 bags of connectors, 12 PVC bend guides, and then you got to throw in your thermostats, zone actuators, whatever you need. Also important is any special tools that might be associated. All right, I'm going to skip these other examples. Rowel panel is a over-the-floor installation technique. It uses extruded aluminum panels. It is very efficient dry installation. It is expensive. It results in a 5/8 inch thick flooring on top of your subfloor that you have to account for. But the key portion for this presentation is that they have a material estimator spreadsheet. As you can see the printout here on the left, most of the dry systems, besides just stapling up, will tell you exactly how many panels you need for a given area. I shouldn't have said exactly. They're giving you the best estimate, and it's overestimating just a little bit to make sure you have enough, but it gives you all the different factors that you need to size the system correctly. So this one's for Rowel panel. They have them for all the different systems. This system gives you the plates, the return bends, and then the plywood furring strips that you may or may not want to provide yourself. And as you can see, material estimator spit out the different amount of pieces you need for each. Same deal for the gauge plates that we mentioned before. As you can see, they give you a 0.6 and a 0.3 multiplier. Again, those are coming from the spec sheets on the different parts. That's just another, we discussed most of these installations, so I'm going to skip through these for time's sake. In summary, you calculate your pipe and the fasteners based on the installation type you're using, then calculate the manifolds based on the number of circuits you need, and then they show Rowel panel here. Any special installation technique they're using is going to have some additional parts associated with it. And then you can package that with your circulators, your expansion system and whatnot, and you got your full system. All right, quickly, I know everyone's trying to get out of here. It's 1 o'clock. I'm going to show you a couple more things I just wanted to touch on to kind of help you when you're estimating here. Okay. All right, the first and foremost thing you want to consider when you're estimating a radiant project is just the feasibility of it in general. A lot of times, a customer, whether it's a client and you're an engineer or you're at a customer's house, they'll want radiant for a certain area, and it may always not be plausible. Even if you're installing radiant in other portions of the house, you might find a zone where, a distant bathroom on the third floor that it just would make sense to throw an electric mat in there instead of running piping and an installation. So just stand back and examine the feasibility of the system before you start. You're going to need a heat source, or if you're doing cooling source. You're going to need to be running piping to and from the zone. You're going to have to decide on an installation option. This picture right here, they put that route panel system I was discussing over an older abandoned radiant system. The other things you need to consider are just how the space is being used, how the output or what kind of output they're expecting or requiring, and then the cost of the system is obviously high up front, but lower over the course of, over the use of the system. And along those lines, the expectations, as I mentioned, the output of the system, what they're looking for, and the comfort, depending on, if it's a indoor system, snow melt, etc. Quickly here, the output of these systems is often limited by the floor covering and the installation type. As I mentioned, if you're doing an underfloor system, the efficiency is much lower, the amount of output you can get out is much lower. And then if you're not using the aluminum plates, it's even worse. The other thing to consider is the floor covering. With a wood floor, they may only be able to handle certain temperatures. So that could be a limiting factor in how much heat you can get out of it. And most radiant companies have all this tabulated. This is showing the R values. As I mentioned before, you have to insulate 5 times that on the bottom side. Most of this is tabulated, but you're going to want to check this with the actual flooring that you're using on the job to make sure that it matches. A lot of them, as you can see in this picture, engineering hardwood can take a higher heat and has a lower R value. So a lot of the newer products are actually beneficial to a radiant system. As far as expectations of performance, if on a regular slab indoors, to stay within an acceptable kind of surface temperature, you're really only going to be getting about 40 BTUs per square foot out of the system. And if you're doing an underfloor system where you have a wood floor, that's probably limited to only about 20 BTUs per square foot. As far as the design standard, if you're in a bathroom or you're just doing floor conditioning, meaning that the radiant is not the main source of heat, you're going to be designing for about 15 to 20 BTUs per square foot. In a snow melt system, since you're dealing with much lower surface temperatures and a bigger delta T, not necessarily a bigger delta T in the water system, but between the surface of the concrete and the air, you can definitely shove a lot more heat into that slab. You can go over 250 BTUs per square foot. In the Chicago area, regardless of the application, for the most part, 125 BTUs is not only acceptable, it's a very good number to use for estimating. We might go higher than that if it's a helicopter pad or a critical area, or if there's less insulation available. But in general, 125 BTUs per square foot is a great starting point for snow melt. And there's going to be some specialty applications, such as like a pool deck, where it might be, you might design at 50 BTUs per square foot. You can't go too much higher on pool decks because they can get overheat and burn people's feet. As far as, tennis courts or turf conditioning, those are a little more specialized. So if you're working on one, you're welcome to contact us and we can help you kind of get a ballpark number. Most manufacturers can do the same as well. The next thing you want to consider is your heating or cooling source. If you're working with high temperature heating, you're going to need to do some mixing. There's lots of different ways you can do that, but that's definitely something you need to consider. Here on the right is a little module that bolts onto Ray house manifolds that does supply and mixing. If you're doing low temp heating with geothermal or condensing, that's perfect for a radiant system. You don't have to worry about any mixing there. If you're doing cooling, there are special considerations you need to take. Most manufacturers will recommend that you need to be in at least 5/8 inch tubing or higher. They do have tighter delta T's, tighter tolerances, and most notably, on the control side, you need to be cognizant of the dew points and whatnot to make sure there's no sweating going on. And then there may be some specialty applications where you're using the heat reclaim from a chiller, or you have a small basement zone that it's not worth installing a boiler, so you're just going to run off the side of a heat exchanger, or sorry, of a water heater with or without a heat exchanger and whatnot. So there's a lot of different applications, but you need to make sure that you have a viable heating or cooling source, or they're willing to install one. Some starting points, as I mentioned before, for laying these out. And if you guys would like, I can definitely send you a copy of these slides. But if you're for a radiant slab, my starting point is always 1/2 inch Raupex in 300-foot loops with 12-inch spacing. If you get over 2,000 square feet, that's a rough break off. I mean, you can definitely swap these in and out depending on the application and how you want to do it. But if you have zones over 2,000 square feet, I would definitely consider switching to a 5/8 inch tube with a 400-foot loop. Again, these are kind of for zoning, not your total job. So if you have zones that are much smaller that total up to a bigger project, you still want to be doing smaller loops for smaller zones. And underfloor heating, it's about the same, but you want to use 8-inch spacing in your calculations because of the joist space. A lot of the overfloor systems use this 8-inch spacing as well, but their estimators will help you calculate all that anyway, as I list here. Snow melt, a good starting point. If you're under 1,500 square feet, 200-foot loops with 5/8 inch. Or if it's over 1,500, 325 with 3/4 inch. And we use or recommend 9-inch spacing for snow melt. All right, so just a checklist of things you need to make sure you're including when you're estimating. As far as the rating itself, the pipe, the manifold connectors, the pipe ends, and the fasteners. That's your system there. Manifold enclosures if you need them. Cabinets, if it's outside, a manifold vault type thing, or a landscaping box. A lot of times in houses, we recommend just sticking them in the back of a closet and then putting in the wall cavity, and then just using a regular access panel. Or the easiest I've heard, Bill Bailey in our office always recommends, just put a return air grill over it. It's easy to get to, and it's in the closet, so no one's going to care. And then your insulation, and then your heating and cooling source. If you need heat exchangers, if you're using a boiler, you might have primary, secondary, tertiary piping. If you have a lot of small zones, you're probably going to want a buffer tank to prevent cycling. Your expansion system, you're either going to want your fill valve or a glycol feeder, expansion tank, air separator. And then your circulation control. We didn't get too much into zoning, but as I mentioned a couple times, you can do manifold mounted actuators. You can do an actuator for the whole manifold, or you can zone with pumps. And depending on the size of your system, that's usually the determining factor of zone pumps versus actuators. With the high efficiency variable speed pumps these days, actuators are making more and more sense just for energy's sake. Slab sensors or snow moisture sensors. You always want to be cognizant of if you need those. In indoor systems, depending on the flooring type that's going over it, usually determines if you want a slab sensor. If you're just doing a garage or an extra basement area, slab sensors with a concrete slab aren't as important. If you're doing a wood floor that's sensitive to temperature, you definitely want to be including slab sensors. And then if the system is in a commercial building and there's going to be a building automation system, you need to touch base with them to see who should be supplying the sensors, what sensors they want, zone valves, etc. This is just a cool little photo on the side here. They've installed the radiant actually between two pieces of mesh. They installed a piece of mesh, used nylon ties to put it down, and then put another layer over it for the concrete because they're using a thicker slab. And as you can see, they got that big screed on there, laser screed on there, smashing down the pipe, no problem, super resistant. But just another, you want to make sure that you're accounting for all that mesh, all the fasteners, and then as you can see over on the left, got the manifolds there to keep it under pressure, and the pipe ends. Some reference options. If you go to Rayhau's website, you can kind of work your way into the plumbing and mechanical section. They have a great resource center here. If you see up at the top, it's sorted by specifications, technical bulletins, submittals, instructions, profiles, or you can just search the literature by product. They have different installation manuals. They have specs on all the different materials if you need to submit to a client. They also have estimating resources for the different installation methods. And then they also have some of these presentations. So I went through some of them pretty quickly and selected slides. You can certainly go and find them in their entirety here. They also have a whole YouTube channel that you can access from here, which is great. This I just was made aware of yesterday. It's a pretty new tool that they have, but based on, this is Rayhouse specific, you can see in the gray boxes here, they have the different types of installations. And basically you pick which type you're using, enter in the square footage, and it does a little calculation for you. Otherwise, you can pull up the spec sheet on any of those, and it calculates, and it'll show you how to calculate it. But this is a nice quick tool, especially if you're just doing a slab row report. You just stick it in, and it'll tell you, everything that you need to include there. Here's some contact info for myself, and I have Bill Bailey and Bill Chanel on here. They are the product managers for our different hydronic lines and have been working with hydronic systems for probably, I think 30 and 20 years respectively. So a lot of experience here. I'm available in the office at any time if you need help, either assisting with an estimation or submittals, whatever it would be. Feel free to contact us. But that sums up our presentation here. I didn't get much of any questions, but feel free to contact me at my email or phone there if you guys have any questions or concerns, or if you have a project that you have specific questions on, we're happy to help. Thanks for your time. I'll stick on here for another minute or two if you guys have questions. Otherwise, thanks for your time.